additive, so you get lost on these. You can just write them out like this. So is it 4 times what? 6 over 5 squared, like this, and it keeps going, right? This is where you need to remember log rules. This is where you need to remember log rules. What does plus mean between logarithms? It means multiply, right? So so this goes on forever, right? But this is really ln of what? 1 times 3 times 2 times 4 times 3 times 5 times 4 times what? 6, all over what? 2 squared times 3 squared times 4 squared times 5 squared. And it keeps going, right? Do you agree? All of that goes away. And what? Everything goes away. What's the only thing that's left? What's the only thing that's left? ln of 1/2. All done. It's awful. This is terrible. This is just a definition that you need to be comfortable with and that you will get more comfortable with practice. A power series about x equals a is a sum of constants times powers of x minus a. So these are constants, and then you have x minus a squared, all the way to x minus a to the n. Very similar in a way to polynomials. It's just a classification. How many terms can there be? Well, in this case, how many are there? An infinite number. So this is a special type of infinite series. We're going to work with them. We're going to work with this type. We're going to work with this type. These series, the difference is that, like this series right here, this is numeric. This is strictly numeric. In this case, there's an x in it. C is a constant, and so is a. X is in it. The reason we're going to look at these, one of the things we're going to spend time doing is sometimes these converge and sometimes they don't. That's exactly the same question we were asking before with 9.1 to 9.4. When do these series converge? When do they don't? When do they not? When do they don't? When do they not? Yeah, when do they? Who knows? For a fixed value of x, if this sequence of partial sums converges to the limit of L, that is, the partial sums go to L, then we say that the power series converges to L. What's really interesting about these is that for some x values, they will converge, and for some x values, they won't converge. What does this mean? What does this mean? Specific example. Determine whether this power series converges or diverges for these values. So, like with that bonus question we just did, what's really helpful is list some terms to see what this looks like. So what does this mean? If x is equal to -1, what does that summation become? It becomes the sum from n equals 0 to infinity, that doesn't change, of -1 to the what power? -1 to the n over what? I'm just having a hard time with this, sorry. Not n, 2 to the n, exactly. Now, let's list these out. When n is equal to, you notice how it starts at 0, by the way? That is okay, that can happen. When you plug in n equals 0, what is that number? What comes out? 1, correct? Yeah. When I plug in 1, what do I get? Minus a half? And then what is it going to be? Plus what? Plus 1/4. Minus what? And you can actually tell me, does that converge or not? Converges. Why? Because there's two ways. What? It's a geometric series. Geo and the absolute value of 1/2, which is its ratio, is less than what? 1. You see what I mean? Yeah, and it's alternating. And it's going to 0. It's an alternating series that goes to 0, so it's definitely going to converge. Absolutely. Let's look at this one. We plug in 3 instead. So if we plug in 3 instead into this, I'll make it a little bigger to make it easier to write. We end up with n equals 0 to infinity of 3 to the n over 2 to the n. Plug in 0, what do you get? 1. And plug in 0, you get 1. Anything, that's okay. Plug in 1, what do you get? 3/2. And then what do you get? 9/4. And then what do you get? 27/8, yes. Does this converge? Diverges, why? Geo, yep, and the ratio which is what? 3/2 is greater than 1, exactly. So here's the thing. This is the same sentence except a different value for x, a different value for x, a different value for x. So depending on the x value, it could converge or it could diverge. Are there going to be some where it doesn't matter what you plug in, it's always going to converge? Yes. Are there going to be some that are always divergent? Absolutely. We're going to look at ones primarily where it gets really interesting. It'll converge for some x values and it'll diverge for, you make all the decisions. Write that in summation notation by yourself, see what you can come up with. There's more than one way. To infinity with you so far, yep.
Of -1
To the
n minus 1.
To the n minus 1, yep.
Times x minus 2 to
X,
2n plus 2.
x minus 2?
Yes.
X minus 2?
Yeah.
To the what?
To the 2n plus 2.
Like this?
X minus 2 infinity.
Oh, I'm sorry. You know what? I'm sorry. I have the screen frozen. Sorry. To infinity of -1 x minus 2 to the what?
2n plus 2.
Plus 2, yep.
1 is to the n minus 1.
Thank you. And it's over what?
Over n plus 1 in parentheses to the, or squared.
Squared. Awesome. Awesome, awesome. I think that's the exact same one the book likes. They have preferences sometimes. That's exact. Actually, you know what? They start at 2 and just make it n squared in the book. I never said you couldn't. I just said I'd prefer. Here's why. Here's why. When I give a test to 10 people and there's a value for x, if I don't plug in a value for x and I just listed all the terms, you'd have something with x in it, plus something with x in it, plus something with x in it. The partial sums would just keep on adding higher powers of x. Do you understand that, everybody? So like S1 is just the first term. What does S2 represent? The first 2 terms added together. What does S3 represent?
First 3 terms.
The first 3 terms, the first 4 terms. So you end up getting a longer, higher powered rational function. You with me so far? Yes. You know, the big polynomial over a big polynomial. And as you add terms to it, the power goes up on the numerator denominator in this case. Are you with me so far? So here's what we're going to look at. Let's look at a slightly different one here. Let's look at this one. This one right here. You could take this as long as you might have this huge long power series. You're going to write it as a summation, like we just practiced a little bit, and then you're going to run the ratio test on it. The thing is, when you run the ratio test, there's going to be an x coming along for the ride. So when you do the limit, what's going to be in your answer? An x somewhere. Maybe not. Maybe it cancels out, but there might be an x in there. For it to converge, whatever you end up with has to be less than 1. So you tell me then what values x can be so that the ratio is less than, and then that's your radius of convergence. You're going to run the ratio test, and then you get to be told, you are told directly what values of x give you a ratio less than 1. This is a big idea. So let's do an example. Let's do an example. Let's do one in order here. It even tells you. It says, show that the following power series converges for all x. For all x. Is it right on the first try?
Yes, because we're so smart.
We're so smart. We're so smart right now. We're so smart right now. Okay, so now we run the ratio test, which is the limit as n goes to what? Infinity of the absolute value of the next term over the absolute value of the current term. You remember this? So what would be the next term if we wrote this out? N plus 1 over, okay, over, sorry, I'm just trying to get this in here, over, come on, over n plus 1 factorial over what? Over n factorial. And this whole thing is like that. Great. So what does that equal? That equals the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial times what? Over what? X to the n. You with me so far? What cancels here? So what are you left with on top? You're left with x up top. And what are you left with on the bottom? You're left with just n plus 1, and it's like this, right? Keep in mind, x is a static number. Like you choose x. X is it's not infinity. It's not going anywhere, right? How big could x be? As big as you want, but it's a fixed number, right? What about n? And n is growing even bigger. Whatever you pick x as, you have to go further for this one. Whatever you pick x to be, you have to go further in the denominator. So what does this limit go to? Regardless of what x is.
0.
This goes to 0. So what does this tell us about the radius of convergence? Does it matter what the radius of convergence? It is an infinity. The radius of convergence on this one is infinity because no matter what x is, this is going to be less than 1. No matter what x is, this is going to be less than 1. So no matter what you plug in, here's the basic logic if you want to believe it. Look at the original thing here. That looks incredibly big, right? It looks like this is getting huge, right? But what gets way bigger faster? Factorial gets way bigger, way faster. This just proved it.
So why are supposed to be infinity?
What? Do you see it over there? So you see this. What's the only thing you have to decide? Exactly. So it's, oh man, do you see what it's doing now? Fantastic. That's just great. Hold on one sec. I need to close this and reopen it.
Why does it do that?
It was writing even though I was like half an inch off the screen. Hello. You're being very cooperative today. No, you're not. Okay, it's going to be a little messy until I restart. I'm sorry. So it's going to be this, -1. This is highly, look how, ugh. What is, ew.
I think you should restart it.
I will, but I don't want to lose the time, so I'm just going to do it on the board.